Hello! In this video, we are going to prove the following theorem. Let a and b be subset of real numbers. F is a function from a to the real numbers, and g is a function from b to the real numbers, such that the range of f is a subset of b. Now, because the range of f is a subset of b, this tells us that g compose f is going to be a function from a to the real numbers. And if we recall, g compose f is defined by g compose f of x equals g of f of x. Now, we're supposing that psi is a cluster point of A. And this means that psi is a cluster point of the domain of f, which means we can ask ourselves about the existence of the limit of f at psi. And we'll say that limit exists, and it's equal to eta. And we'll assume eta is a cluster point of B. And that means eta is a cluster point of the domain of G. Therefore, we can ask ourselves about the existence of the limit of G at eta. We'll say that limit exists and it's equal to L. Further, we're going to assume that there is an open interval I containing psi, and given any element x in both A and I distinct from psi, we have that f of x is not equal to eta. Then, the limit of the function g compose f at psi exists, and it's equal to L. Now, a reason why you might find this theorem useful is because from it immediately follows that the two common definitions for the derivative of a function are equivalent. And here's what I mean. If we're given a function f, then one definition for the derivative is as follows. The derivative of f at c is defined to be this limit, if it exists. Here's the other definition. The derivative of f at c is defined to be this limit, if it exists. Now, you can use this theorem to rigorously establish that these two definitions are equivalent. And when we say equivalent, we mean if this limit exists, then this limit exists, and the two limits are equal. If this limit exists, then this limit exists, and the two limits are equal. So that's the idea, right? I'll make a video in the future proving that these two definitions are equivalent, and I'll give more details. But that's a reason why you might find this theorem useful. So now, let's get into proving this theorem. Now, the whole goal is to prove this limit is true. And let's just go back to the epsilon delta definition of a limit to prove this. If we recall, by the epsilon delta definition of a limit, this means the following. It means this, right? For every epsilon greater than 0, there exists a delta greater than 0, such that for all x in the domain of our function, if 0 is less than the absolute value of x minus psi, which is less than delta, then the absolute value of g compose f at x minus L is less than epsilon. So, to prove this limit, all we have to do is prove this statement. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a delta greater than 0 such that this is true. Okay, now we are given that these two limits are true. And by the epsilon delta definition of a limit, these two things mean the following. Right? This limit means this first statement, and this limit means this second statement. So, because we are given these two limits are true, this means we are given that these two statements are true. Now, this second statement works for every positive real number. So in particular, it must work for the positive real number epsilon that we just introduced. So taking epsilon to be the epsilon we just introduced, we have that there is a delta greater than 0, such that for all y and b, if 0 is less than the absolute value of y minus eta is less than delta, then the absolute value of g of y minus L is less than epsilon. Now, I'm going to call this delta 1. Right, so just like that. And also, since this limit is true, this means we are given that this first statement is true. And this first statement works for every positive real number. So in particular, it must work for the positive real number delta 1 that we have in our proof. So taking epsilon to be delta 1, we have that there is a delta greater than 0, such that for all x in A, if 0 is less than the absolute value of x minus psi is less than delta, then the absolute value of f of x minus eta is less than delta 1. Now instead, I'm going to call this delta 2. And we're not going to need these two definitions anymore. Remember, the whole goal is to find a delta greater than 0 such that this is true, because that will prove this limit, which is exactly what we want to prove. Now, in order to define delta, it turns out it's going to be nice if we define delta small enough so that the delta neighborhood of psi is contained in this open interval I. Now, there are 4 possibilities of what I could look like. One possibility is that I is bounded, and so in this case, it would look something like this. Another possibility is that I is only bounded below, so something like this. Another possibility is that I is only bounded above, so something like this. And the final possibility is that I is unbounded, which means I is the set of all real numbers. Now, we know that psi belongs to I, so I'm just going to arbitrarily label psi in each of these 4 cases. Now notice, no matter which form I has, we can always find an open bounded interval containing psi, which is a subset of I. For example, that open bounded interval in this case could just be this. In this case, it could just be this. In this case, it could be that. In this case, we could just choose this. So no matter which of these 4 cases we have, we can always find an open bounded interval containing psi. And this open bounded interval is a subset of the larger open interval I. And so we'll call this open bounded interval I prime, where the bounds are a comma b. Now, since psi is an element of a comma b, this means a is less than psi is less than b. So now, all we have to do is define delta, so that delta is the smaller of delta 2, b minus psi, and psi minus a. So the claim is, with this choice for delta, we can show that this statement is true. And so, since we're trying to prove a statement about all x in A, let's give ourselves an arbitrary x in A. And from here, we would like to show if this is true, then this is true. So let's suppose that this is true. Now, we know by definition of delta, delta is less than or equal to all 3 of these guys. So in particular, delta is less than or equal to delta 2. And since delta is less than or equal to delta 2, we have that 0 is less than absolute value of x minus xi, which is less than delta 2. And because of this inequality, we can use the fact that this statement is true, right? This statement works for every element in A. So in particular, it must work for the x that we introduced into our proof right here. So taking x to be the x we introduced into our proof right here, we have if this is true, then this is true. Well, we know that this is true. That's what we have right here. Therefore, we can conclude that absolute value of f of x minus eta is less than delta 1. Now, we would like to use the fact that this statement is true next, because we know that this statement works for every element in B. So in particular, it must work for f of x. So taking y to be f of x, we have if this is true, then this is true. And we want to show that this is true. That is our whole goal. Now, we don't actually know at this point whether or not this is true. We actually only know that the right-hand inequality is true. That's what we have right here. We don't know that the left-hand inequality is true, right? In order to show that this left-hand inequality is true, it would suffice to show that f of x is not equal to eta. And that's precisely what our extra hypothesis is used for. It's to show that f of x is not equal to eta. So, to show that f of x is not equal to eta, we are going to show that the x that we introduced into our proof is an element of A intersect I, and x is distinct from xi. So at this point, we know that x is an element of A. That's what we have here. It's also not difficult to see that x is distinct from xi, right? That's just due to this inequality. Since the absolute value of x minus xi is greater than 0, this means that the distance between x and xi must be greater than 0, and so x and xi cannot be equal to each other. So x is distinct from xi, so all that's left to show is that x is an element of I. And that comes from the fact that we restricted delta so that delta is less than or equal to b minus xi and xi minus a. Because delta is less than or equal to both of these guys, we know that the absolute value of x minus xi is less than these two guys. So since absolute value of x minus xi is less than b minus xi, well, in the language of absolute values, this is equivalent to saying x minus xi lies between the negative of b minus xi and positive b minus xi. Well, if we look just at this right-hand inequality and add xi to both sides, we see that x is less than b. In a similar way, since the absolute value of x minus xi is less than xi minus a, then again, in the language of absolute values, this is equivalent to saying x minus xi lies between the negative of xi minus a and positive xi minus a. Now, if we focus just on the left-hand inequality, well, the negative of xi minus a is equal to a minus xi. And if we add xi to both sides, we see that a is less than x. So we have that a is less than x is less than b. That tells us that x is an element of I prime, which is a subset of I. So x is an element of I, and therefore this condition is satisfied. So the x that we have in our proof satisfies all three of these conditions, so we can conclude that f of x is not equal to eta. And since f of x is not equal to eta, surely the absolute value of f of x minus eta is greater than 0. So this is true, but also we know that this guy is less than delta 1. And now let's remind ourselves, we know that if this is true, then this is true. Well, we've just shown that this is true, so we can conclude that this is true. And that is exactly what we wanted to show, right? We know g of f of x is equal to g compose f of x by definition. So this is exactly what we wanted to show. And so we have proven this entire statement, which means we have proven that this limit is true. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.